So now we have a complex function that is differentiable at a point, say z(o). There is a point which lies in the domain of that differential this complex function. At that point, the function is differentiable. If in addition to being differentiable at z(o), if the function is also differentiable in some neighborhood of z(o), that means one, it should be differentiable at z(o), exactly at z(o), it should be differentiable. Plus, if it is differentiable in a neighborhood of z(o), however small that neighborhood may be, then the function is said to be analytic at z(o). Analytic at z(o). So there is a difference between differentiability and analyticity. That is, in analyticity we have two things: function differentiable at z(o) plus function differentiable in its neighborhood. While it's at differentiability, we are concerned about only this differentiation at a point. That is how complex differentiation is a bit more restrictive, more restrictive in the sense that you not only need the function to be differentiable at a point, you also need it to be differentiable in a neighborhood of that point. Now, having said this, and since in our last this lecture where we discussed sufficient conditions for a complex function to be differentiable, we found that the derivative of a complex function is at the end of that unit we found at the end of that lecture we found that derivative of a complex function is given by we derived this expression that it is given by u ux ux minus I ux minus I uy. This we derived at the end of that. We can give it several these forms. We can express it in terms of several these forms. For example, using CR equations. For example, I can use CR equations to replace uy here. You know that ux by CR equations, ux is equal to vy, number one. Number two, second relation is uy is equal to minus vx. If I have uy here, if I replace it by this, then I will get another expression ux minus, and then this minus that plus I uy I ux vx I vx. So this is in terms of both these partial derivatives with respect to x. This is a mix of the two, and we can even have expression in terms of partial derivatives with respect to y. For example, by replacing, instead of replacing this, we can replace this. If we replace this ux equal to vy, then we have vy in this place vy minus I uy. Now that is up to us which we find convenient. We can use. We will be mostly using this mostly, but it is not necessary. Any one of them you can use. Now we are now in a position to take up problems based on these CR equations and continuity of partial derivatives. Now, first problem that we will examine, for example, let's take this interesting function fz is equal to mod z square, that is z complex conjugate, z bar. Okay, we will examine whether this function is differentiable at some point or is at some point, and then we will also examine whether it is differentiable in the neighborhood of that point as well. Let us see. We have the question may come like this: examine the analytic nature of this function. or it may come in many other these forms, but our approach will be the same. It is something like this. Suppose you have fz is equal to z bar, that is equal to x plus iy, x plus iy into x minus iy. Okay, then that is equal to x square plus y square, x square plus y square, plus there is no imaginary part left. We can write, however, plus I I0, I into 0. This is imaginary part. Therefore, u is equal to here x square, that is real part of the function, that is equal to x square plus y square. V is equal to 0. Now let us examine whether it obeys CR equations or not. For that matter, let us go here. Again, let me show you. U is equal to x square plus y square, and v is equal to 0. First of all, CR equations. For that matter, let us differentiate it with respect to x. We will get 2x. While we differentiate it with respect to x, we have to keep the other constant. We have to treat it as constant. Similarly, uy. Now we will treat x constant, so we will get 2y. What about this Vx? That will be 0. Vy again 0. Now the question, CR equations. CR equation first, CR equation second. First tells us that Ux should be equal to Vy. Second tells us that Uy should be equal to minus Vx. So let's examine whether these are obeyed here or not. Looking at this ux, this is 2x, 2x equal to vy, vy that is 0, 0. 2x equal to 0, which is absolute, which is not actually true except for x equal to 0. This means that x equal to 0. That means at x equal to 0, ux and vy are equal. Ux, 2x, and vy are equal only at x equal to 0. Similarly, let us go to this. Uy, 2y is equal to minus vx, vx is 0. This means again that y is equal to 0. This means then we will conclude that CR equations are obeyed only at the origin 0, 0, where x is equal to 0, y equal to 0. Only at that point. This means like this. This is x, this is y, and CR equations are obeyed only at this point, only at, not here, not here, not in the neighborhood. Even though you can see, you can yourself see, even though we have these, we have ux, which is equal to x, is a continuous function, uy is a continuous function, vx is a continuous function, vy is a continuous function. Something I would like to tell you about this continuity. You can look at a function and immediately decide whether it is continuous or not. Immediately determine whether it is continuous or not. We have some guidelines. The first guideline is that if a function is constant, suppose you have a function that is constant, if a function is constant, it is continuous. Now, you see, suppose a function is constant like this, it is continuous everywhere. Fx is equal to continuous, that is continuous. If a function is equal to, if a function is identity, fx is equal to x, it is again continuous. Something like this, continuous. Then similarly, if a function is say some power of x, say x square, again it is continuous. X cube, again it is continuous. X4, again it is continuous, and so on. That means now if a function is say, suppose for example sine x or cos x, it is continuous. Sine x, cos x, you can yourself see graph of sine x, for example, it is continuous. Nowhere there is any gap, nowhere there is any hole or this discontinuity. Same is the case with cos x. This too is continuous. e raised to x, that 2 is continuous. Here is the graph of e raised to x, e raised to x equal to 0, equal to e raised to x is 1, and then as x increases, e raised to x increase rapidly, e raised to x. Then you have all the functions, all those functions which are uh, obtained by addition of these continuous functions, or subtraction of these continuous functions, or multiply these continuous functions, or dividing these continuous functions, are also continuous. The sum, difference, product, quotient, or of these are all these continuous functions, provided keep but we have to take care of the denominator. Nowhere should be equal to 0, other the function will blow up there. Now that means, for example, suppose we have a function like this, f(x,y) is equal to a combination of so many functions. Say it is equal to sine 2x, sine 2x into x square plus 9 into for example, x square plus y square divided by x square plus 1. This is continuous, this is continuous, this is continuous, this is continuous, hence the whole thing is continuous, provided only that the denominator should not be equal to 0. Of course, then all polynomial functions will be continuous. Say for example, you have x cube minus 3x square plus 4x plus 5. The reason is that each term of this is continuous, hence this fx is continuous. So one more thing that I would like to tell you is that compositions of such functions are also continuous. For example, FOG or GOF of these functions, they are also continuous. And then one more last thing, that is, for example, if you have log x, if x is real number, for x to be if x is real number, then this log x is not defined for x equal to 0, or neither is defined for x less than this 0. You can yourself see that e raised to minus infinity is equal to 0. That is equal to 0. That means if you change this into log, then it becomes log 0 to the base e is equal to minus infinity. But minus infinity is something which we don't count as number. So it is not, log 0 is not defined. Okay. Now, except for this log 0, if x is greater than 0, then it is defined. So for all x greater than 0, log x is a continuous function. This was something about continuity of functions. You need not prove continuity of functions now and then, often. I mean, you need not prove them often. So you can rely on this inspection. The mere inspection can tell you whether the function is continuous or not. Let's now move ahead. Our function was, let us see, we were actually discussing this function, this z fz is equal to z bar. That is this was our fz is equal to this, and then we reached here. This was equal to this, and then lastly we were here, and then what we found? We found that the CR equations are obeyed only at the origin, even though all the partial derivatives are continuous. Since CR equations are only obeyed at the origin, hence the function is differentiable at origin only, but it is not analytic function because it is not differentiable in any neighborhood of this function, of this origin. So that we decide then, we find that this function is not analytic at 0. Even though it is differentiable at 0, but we cannot say it's analytic at 0. To be analytic at 0, it should have been differentiable in a neighborhood of this 0, neighborhood of this. Now, let us go to another example. Our next example is, for example, next example is a trigonometric function that is, say, sine z, fz is equal to sine z. We want to see whether it is analytic or not. Now, for that matter, we need some formulas, hyperbolic functions, or uh, these are our two hyperbolic functions which I am going to define in this part of the screen. I have first hyperbolic sine. Hyperbolic sine. Hyperbolic sine. Just a minute. Sorry. Hyperbolic sine. I have sine h. We call it hyperbolic sine, or sometimes we call it shine x. Shine x. Anyhow, whether you call it sine, hyperbolic sine, or shine x, that does not matter. You are free to choose. Now, basic definition is e raised to x minus e raised to minus x divided by 2. Now, this is definition of sine x. Cos, hyperbolic cos has this definition: e raised to x plus e raised to minus x divided by 2. Now, we can derive a relation between these and corresponding trigonometric ratios. For example, there is a relation between sin x and this sin x. The relation is this: suppose you have, if you have something like this, for example, if you take e raised to ix minus e raised to minus ix. This is an expression for us. E raised to ix plus e raised to ix. First I will take plus, then minus, divided by 2. I will use Euler's theorem for expanding this and this. In terms of Euler's formula, this is equal to cos x plus I sin x, and this is equal to cos x minus I sin x. I sin x divided by 2. I sin x minus I sin x, these two will cancel. These two cancel. We are left with 2 cos x divided by 2. 2 cos x divided by 2. 2 and 2 cancels out. We get cos x. Cos x. What do we find then? That cos x is equal to this. I will need the full page, so let us postpone this. We will first get these formulas which we are going to use. Cos x is equal to, e raised to ix plus e raised to minus ix divided by 2. Similarly, you can prove it yourself that sin x can be written as ix minus e raised to minus ix. Look, there is plus, there is minus, and there is one more thing, that is 2i. You will yourself, if you expand this by using Euler's theorem formula and this Euler's formula, then you will arrive at this formula. Naturally, you will arrive at this formula. Now, after this, now suppose there is an interesting relation, that is, if you this is, first of all, this is sin x, hyperbolic sin x, hyperbolic cos x. Let's differentiate them here. Let's find their derivative. Now, derivative of this means derivative of this. And what is derivative of this? Derivative of e raised to x is e raised to x minus derivative of e raised to minus x is that minus will simply come down and it will become e raised to minus x divided by 2. But what is this? This is, you can check it. This is hyperbolic cos. So it is hyperbolic cos. Why from did you get this hyperbolic? By differentiating hyperbolic sine. So derivative of, or I can write derivative of hyperbolic sine, derivative means dash here, that is equal to cos x, hyperbolic cos. No negative sign. Similarly, suppose I differentiate this derivative of, let's take now derivative of cos, hyperbolic cos, and see what it will come out to be. When we differentiate this, it is e raised to x. When we differentiate this, it is e raised to minus x divided by 2. What is this equal to? E raised to x, e raised to minus x divided by 2. That is simply sine x, hyperbolic sine x. Important thing that to remember is that hyperbolic sine is converted into cos, hyperbolic cos is converted into hyperbolic sine. But unlike trigonometric, corresponding trigonometric formulas, there is no problem of plus and minus signs. All are positive. Both derivative of sine, hyperbolic sine is positive, derivative of hyperbolic cos is positive. Having done this, and then the last thing that I will need, that it will be relation between hyperbolic sine and hyperbolic cos. Suppose I have hyperbolic this cos, something like this, or hyperbolic this trigonometric cos iy. Instead of cos y, let me have cos iy. This means that you know that cos y is equal to e raised to ix plus e raised to minus ix divided by 2. You can, for your ready reference, you can see it here. Cos e raised to ix plus e raised to minus ix divided by 2. Now instead of, so I'm sorry, it is cos, let it be cos x. Now instead of cos x, let me replace x by ix or x by iy. Replacing x by iy, what I will get? I will get cos iy is equal to e raised to I, this I into x is to be replaced by iy, so it is iy plus e raised to minus I into iy divided by 2. What is that equal to? Let us see. This is minus e raised to minus y. Then this is plus e raised to I square is minus and plus this, that is, this becomes plus y divided by 2. That is equal to simply ey plus e raised to minus y divided by 2. And what is this? This is simply hyperbolic cos. You can check hyperbolic cos, hyperbolic e raised to x plus e raised to minus divided by 2. Hyperbolic cos, so it is cos y. What do we conclude? Cos iy is equal to hyperbolic cos. Hyperbolic. Let me correct this formula with these formulas. So I have shown that cos iy is equal to hyperbolic cos. What about sine? Let us see. Sine iy is equal to. We will first take this expression for sine x. That is here. Now let us go and see what will be this hyperbolic. Sorry, not this. I want sine iy now. Sine iy. I know that sine x is equal to e raised to ix minus e raised to minus ix divided by 2I. If I now replace x by iy, replace it, I will get e raised to I x iy minus e raised to minus iy divided by 2I. That gives me, this is e raised to minus y minus e raised to plus y divided by 2I. That is equal to e raised to minus y minus e raised to y is equal to, by cross multiplication, 2I sine iy. Now divided by 2I, but 2, we have to keep this 2 here. 2 is to be kept here because this itself is a formula, but it is not hyperbolic sine. There is a difference. In hyperbolic sine you have ey first, then minus e raised to minus y. You can check it here. Hyperbolic sine, ey first minus, use positive first then negative, so you have ey, that is you have e raised to y minus e raised to minus y divided by 2, which we can of course obtain from this by multiplying both sides by minus. That is minus I sine iy. So this is hyperbolic sine. So hyperbolic sine hy is equal to minus I sine iy. Now this formula I will be using along with those, that is I have minus I sine iy, or in terms of this sine iy, if I write it sine iy minus I is to be transposed to this side, and in that case I will have the final formula like this: sine iy is equal to sine hyperbolic sine h y hyperbolic sine divided by minus I. Now we know that minus I is we can bring it here, minus sine hyperbolic sine divided by I, but this minus is equal to I square, is equal to I square sine hyperbolic sine y divided by I and I cancel. What we get? We get sine iy is equal to I sine hyperbolic sine y. So I will write it here. Again, I will record it here. Sine iy is equal to I hyperbolic sine y, sine y, hyperbolic sine y. Again, sine iy, sine, we had it here. We had it somewhere here, not here, somewhere here. So we have now this here sine iy is equal to I sine y, and here you find cos iy is equal to cos. It is as if cos absorbs I, while as sine cannot absorb it, it comes out. We will be using these two, all these relations here. So let's now go to examine the analytic nature of sine z. Fz is equal to sine z. That gives us sine. In place of z, we can write x plus iy. And using sine a plus b, it gives us sine a cos b, then plus cos a sine b sine iy. Sine x, good, that is okay, cos iy. Now using this formula cos iy, using this cos iy is simply hyperbolic cos, that is cos y, plus cos x, we have sine iy, that is sine iy is equal to sine hyperbolic sine iy is equal to this. What was the final formula for that? That is on this page. Sine iy is equal to I sine I hyperbolic sine y, Now we have I hyperbolic sine y. Now hyperbolic sine y, but with I here. It is sine a cos b cos a sine b cos a sine b. Okay. But I don't need it actually right at this time. I don't need it here. I'm sorry. We don't need it yet. We have so we have simply, this is simply sine. Now just a minute. Sine z is equal to sine x plus iy. Good. Sine x plus iy. And then we use sine a plus b equal to simply the formula of sine a plus b. Sine a plus b is equal to sine a cos b plus cos a sine b. Now using this cos iy is equal to, yes, we have sine x cos y, okay, plus cos x, it is sine iy, we found it, equal to I sine h. Okay, so it is okay. Now this is u. This is u, this is v, u and v. U is equal to therefore sin x cos y. V is equal to cos x sin y. Sin y, this is y here. Now, differentiating, first of all, u is continuous because sine is continuous function and cos 2 is continuous because it is made up of hyperbole, this exponential function. This is a cos. This is continuous, this is continuous. The sum is continuous divided by constant, that is continuous. Same is the case with this. This is continuous function. This too is continuous function. Now, what about this ux? Ux will be equal to, differentiating this with respect to x, keeping y constant, then this is cos x cos y uy, that is equal to uy. When we differentiate it with respect to y, we have to keep x constant, so it will be sin x cos y. Oh, sorry, you have to differentiate this cos y. Cos y becomes simply sine, hyperbolic sine y. You need not worry about the sign here. That is the advantage. Vx is equal to v. Similarly, Vx is equal to, differentiate this with respect to x, then it becomes minus sine x cos. Sorry, you are not differentiating this sine y. Y is to be kept constant. Now, differentiating with respect to y, you have to differentiate this with respect to y, not this. That is a common mistake that people students make. Now you have cos x, that will remain constant, and sine y, that is cos y. Derivative of that is cos y. Now let us compare CR equation 1, CR equation 1, CR equation 2. In CR equation 1, you have ux equal to vy. Let's check whether they are equal here. Ux cos x cos y equal to vy cos x cos y. Good. They are equal and equal. Now, CR second, that is uy now equal to minus vx. Now let us see. Uy is this, and then Vx is this. Yes, exactly verified. Again, same. This means that sine x, it obeys necessary condition. And since looking at the derivatives now, partial derivative this, partial derivative this, partial derivative this, all of them are continuous because they are made up of continuous functions. Since CR equations are obeyed, partial derivatives are continuous, hence the function is analytical at every point. There is no restriction. Every point it is analytical. And what is the derivative then? Can you calculate derivative? Yes, why not? We want to calculate f dash z, that is equal to, which is equal to, of course, f dash z of sine z. That means you want this f dash z. Let's look at f dash sine x. F dash, that means f z is equal to, f z is equal to sine z, and you want now f dash z, derivative of this. We have already seen that f dash z is equal to, we have already seen it in our last topic. At the end of that topic, we found it equal to, we had written it somewhere. On our first page, we had ux plus ivx. Ux plus ivx. Let me go to that page. Let me go back. And ux plus ivx. Since we have already found ux is equal to cos x cos y, cos x cos y, cos x cos y plus I vx again. Vx is equal to, what we found, vx cos x cos y. Vx no, minus sin x sin y. Sin x minus sin x sin x sin y sin y. Now I will convert this back, cos y back into cos, and similarly sin y back into sin. Cos x into cos y. In place of cos y, I will write cos iy. This is what I have already proved. Here is that proof. Cos iy, I had written that on some pages. Cos y is equal to cos iy. Cos y is equal to cos iy. Back to this, and then we have minus I sin x. Sin x. I want to convert this sin y as well. Now back to this page. Sin y sin y is equal to minus I sin iy is equal to minus I sin iy minus I sin iy. Okay. Now we have cos x cos iy minus and minus plus, but then I square will again make that minus. So it will ultimately be minus, but I square will be gone. Sin x sin iy. But what is that? Cos a cos b minus sin a sin b. That is cos a plus b iy. But you can easily identify this. X plus iy is simply z. So if fz is sin z, its derivative is cos z. Something, a result that we expect. That is, we will take more these problems based on this in our next video.